The ground crew at Kimbolton Airfield stood motionless, staring at the sky. It was the afternoon of February 8th, 1943, and something impossible was approaching from the east. The formation of B-17 flying fortresses, returning from their mission over Germany, had long since landed, their crews debriefed, their aircraft being refueled and rearmed for the next day's operation. But one bomber was still out there, alone, struggling across the English Channel on what should have been its final approach hours ago. When it finally appeared over the field, the men on the ground could not believe what they were seeing. The B-17 was flying, if you could call it that, on what appeared to be willpower alone. The entire tail section was shredded, hanging by cables and twisted metal. The vertical stabilizer looked as though it had been put through a shredding machine. Daylight showed through hundreds of holes in the fuselage. One engine was completely dead, its propeller feathered, and motionless. Another was trailing a thin stream of smoke. The hydraulic lines had been shot away, meaning the landing gear would not function normally. The bomb bay doors hung partially open, twisted on their rails. The pilot, Second Lieutenant Harold Fisher, brought the crippled aircraft around for his approach. There would be no second chance. With minimal hydraulic pressure, damaged control surfaces, and two engines barely functioning, he had one opportunity to get this right. The tower had already called for the fire trucks and ambulances. Everyone expected this to end in disaster. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. Fisher lined up his approach, compensating for the damaged tail section that made the aircraft want to yaw constantly to the left. His co-pilot, Second Lieutenant Robert Campbell, was calling out airspeed and altitude. The flight engineer had manually cranked down the landing gear using the emergency system, a process that took over 100 turns of a hand crank. They had no way to verify the gear was fully locked until they touched down. The B-17 crossed the threshold of the runway. Fisher eased back on the yoke. The main gear touched first, and held. The tail wheel, what was left of it, settled onto the concrete. The bomber rolled to a stop. 9 men climbed out alive, shaken but unhurt. When the ground crew swarmed the aircraft to assess the damage, they began counting. Bullet holes, cannon strikes, shrapnel damage. They counted and counted and kept counting. The final tally would become legend in the 8th Air Force. This should not have been possible. Everything the Luftwaffe knew about destroying bombers, everything German fighter pilots had learned through 2 years of combat over Europe, said that this aircraft should have disintegrated over Germany. The amount of damage it had sustained exceeded what any bomber should be able to survive. Yet here it sat on an English runway, its crew walking away. The Germans had spent the previous year refining their tactics for destroying B-17 seconds. They had studied the aircraft's construction. They had identified its vulnerable points. They had developed specific ammunition loads designed to penetrate its armor and ignite its fuel. They had trained their pilots to make attacks from angles that maximized damage while minimizing exposure to the bomber's defensive guns. They knew, or thought they knew, exactly how much punishment a B-17 could take before it fell from the sky. They were wrong, and the story of why they were wrong, why the B-17 flying fortress could absorb damage that would destroy any other bomber in the world, begins not with this single miraculous landing, but with a fundamental difference in design philosophy between American and German aircraft engineers. The Boeing B-17 flying fortress was not an accident of engineering. It was the result of a specific military requirement issued by the United States Army Air Corps in 1934, nearly a decade before the aircraft would prove its worth over Europe. The requirement called for a multi-engine bomber capable of carrying a ton of bombs for 10 hours at over 200 miles per hour. The specifications were ambitious for the era, but Boeing's engineering team, led by E. Gifford Emery and Edward Curtis Wells, went far beyond what was asked. The prototype, designated Model 299, first flew on July 28, 1935. When a reporter from the Seattle Times saw the aircraft bristling with machine gun positions, he coined the name that would stick, Flying Fortress. Boeing immediately recognized the marketing value and trademarked the name. But the aircraft that emerged from Boeing's Seattle plant was more than marketing. It represented a fundamental approach to bomber design that differed significantly from European thinking. American engineers built the B-17 around a single principle: crew survivability. This was not purely humanitarian thinking, though the lives of 10 men per aircraft certainly mattered. It was ruthlessly practical calculation. A bomber that could bring its crew home despite battle damage was a bomber that could fly again the next day. More importantly, it was a bomber with experienced crews who could pass their knowledge to replacements. The aircraft could be replaced. Trained combat crews could not be replaced quickly. The B-17's structure reflected this philosophy in every detail. The fuselage was not a thin aluminum shell wrapped around a minimal frame. It was a robust semi-monocoque design where the outer skin carried significant structural loads, supported by heavy internal frames spaced approximately 20 inches apart throughout the length of the aircraft. The frames were not simple rings. They were complex structures with vertical and horizontal members, gusset, plates at stress points, and reinforcement around critical areas like the wings, root, and tail attachment points. Boeing engineers had designed redundancy into every critical system. The flight controls used a dual cable system. If one cable was severed by enemy fire, the backup could still function. The electrical system had multiple generators, each engine driving its own. If one engine was knocked out, the others could carry the electrical load. The hydraulic system, controlling everything from landing gear to turrets to bomb bay doors, had emergency backup systems that could be operated manually if hydraulic pressure was lost. The fuel system was perhaps the most innovative feature. Each B-17G carried 9 fuel tanks with a total capacity of over 2,700 gallons. These tanks were not simple aluminum containers. They were self-sealing designs developed specifically to prevent catastrophic fuel fires when punctured by bullets or shell fragments. The self-sealing technology used layers of rubber compound that would swell and seal when exposed to fuel, plugging holes automatically. A bullet could punch through a fuel tank, and within seconds, the hole would seal itself, preventing both fuel loss and fire. The Germans, by contrast, had taken a different approach to bomber design. The Heinkel He 111 and Junkers Ju 88, Germany's primary medium bombers, were fast and maneuverable but lightly constructed. German engineers prioritized speed and payload over survivability. Their reasoning was sound for the kind of war they expected to fight: short-range missions with fighter escort over territories where friendly air bases were nearby. A damaged bomber could limp home quickly. Crews could bail out over friendly territory if necessary. By 1943, Luftwaffe fighter pilots had been engaging American bombers over occupied Europe for nearly a year. They had developed tactics, refined their approach, and believed they understood how to destroy a B-17. The accumulated combat experience of hundreds of engagements had taught them what worked and what did not work. German fighter pilots had learned that frontal attacks were most effective. The early B-17E and F models had a vulnerability in the nose section, where only handheld machine guns defended against head-on attacks. A fighter coming in from 12 o'clock high could fire directly into the cockpit and forward fuselage, targeting the pilots and flight deck crew. This approach also maximized the closing speed, giving the bomber's gunners less time to track and fire. The Luftwaffe had also refined their ammunition loads specifically for bomber destruction. The standard load for a Focke-Wulf FW-190 or Messerschmitt Bf-109 included a mix of ammunition types: armor-piercing rounds to penetrate the B-17 structure, high-explosive rounds to cause maximum internal damage, and incendiary rounds to ignite fuel and ammunition. The 20mm cannons mounted on German fighters fired explosive shells that detonated on impact, each hit sending shrapnel through the bomber's interior. German pilots aimed for specific areas. The engines were priority targets. A B-17 could fly on 3 engines, sometimes even 2, but each engine lost reduced its altitude and speed, making it more vulnerable to subsequent attacks. The wings, holding fuel tanks and housing the main structural spars, were critical. A fuel fire or structural failure in the wing would bring the bomber down within seconds. The tail section, controlling the aircraft's pitch and yaw, was another target. Severe damage to the vertical or horizontal stabilizers made the aircraft uncontrollable. Fighter pilots learned to judge when a bomber was finished. Smoke from an engine usually meant fire, and fire meant the bomber would soon fall. A bomber dropping out of formation was vulnerable, separated from the mutual defensive fire of its squadron mates. A. B-17 losing altitude rapidly was finished, unable to maintain the 25,000-foot cruising altitude where the thin air provided some protection from flak. German pilots would report a bomber as destroyed when they saw it smoking, falling, or breaking apart. But increasingly, bombers that should have been destroyed were making it back to England. Pilots would report hitting a B-17 with multiple cannon strikes, seeing pieces fly off the aircraft, watching it drop from formation trailing smoke, only to learn later from intelligence reports that the same bomber had landed safely at its base. The fire had been extinguished. The damage, however extensive, had not been structural. The crew had nursed the crippled aircraft across 200 miles of occupied territory, and the English Channel landed it safely, and after repairs, that same bomber would return to attack Germany again. This was not supposed to happen. The Luftwaffe had calculated that a certain amount of damage would destroy any aircraft. They had seen their own bombers disintegrate under far less punishment. They had observed British bombers go down after relatively modest battle damage. But the B-17 seemed to absorb cannon fire and keep flying. It infuriated German pilots and baffled German intelligence officers, trying to understand why their successful tactics were not producing the results the mathematics predicted they should produce. The answer lay not in German tactics, which were sound, but in American engineering philosophy. Boeing had built an aircraft that could survive damage that would destroy other bombers, and the full extent of that survivability was about to be demonstrated in ways that would become legendary in aviation history. The B-17G, the variant that would become the most numerous and most famous of all Flying Fortress models, incorporated every lesson learned from 2 years of combat over Europe. Boeing had built 15,634 B-17 seconds of all, variants by the war's end, with the G model accounting for 8,680 of them. Douglas and Vega, operating under license, built thousands more. This was not small-scale production. This was American industrial capacity operating at full mobilization. Each B-17G weighed 36,135 pounds empty. Fully loaded with crew, fuel, bombs, and ammunition, it weighed 65,000 pounds. The aircraft was 74 feet 9 inches long, with a wingspan of 103 feet 9 inches. 4 Wright R182097 Cyclone radial engines, each producing 1,200 horsepower, gave it a maximum speed of 287 miles per hour at 25,000 feet. Cruising speed was typically 182 miles per hour. Range with a standard bomb load was approximately 2,000 miles, but the statistics that mattered most were the ones the Germans could not see from outside. The defensive armament consisted of 13 Browning M2 50-caliber machine guns, 2 in the chin turret, 2 in the top turret, 2 in the ball turret beneath the fuselage, 2 in the waist positions, 1 in the radio compartment, 2 in the tail turret, and 2 cheek guns in the nose. Each gun had between 300 and 500 rounds of ammunition. The combined firepower could put out over 6,000 rounds per minute if all guns fired simultaneously. The armor protection was comprehensive. The pilot sat behind armor plate that could stop standard rifle-caliber ammunition. Additional armor protected the top turret gunner and the radio operator. The engines had armored cowlings around critical components. Even the oxygen bottles, essential for survival at high altitude, were protected by armor plate to prevent catastrophic explosion if hit. Every vulnerable system had been identified and either armored or provided with redundant backups. The oxygen system itself demonstrated Boeing's attention to crew survival. At 25,000 feet, the operational altitude for most missions, the air was too thin to breathe without supplemental oxygen. Each crew member wore an oxygen mask connected to a system that could supply breathable air for the entire mission duration. If the main oxygen system was damaged, emergency bottles provided backup. German fighters quickly learned that puncturing the oxygen system could incapacitate a crew without destroying the aircraft, so Boeing engineers had designed the system with multiple redundancies and protected the main lines with armor. The intercom system allowed all crew members to communicate despite the deafening noise of 4 engines and wind roaring past the fuselage at nearly 300 miles per hour. In combat, with gunners calling out fighter positions and the pilot needing to coordinate evasive action, communication meant the difference between effective defense and confusion. The Germans had nothing equivalent in their bombers. German crews used hand signals and shouting, limiting coordination. The flight deck itself was a marvel of instrumentation for its era. The pilot and co-pilot sat side by side, each with a full set of flight controls. If one pilot was killed or wounded, the other could fly the aircraft alone. The instrument panel displayed engine performance, fuel levels, hydraulic pressure, electrical system status, altitude, airspeed, heading, and artificial horizon. The pilots could monitor every critical system at a glance. If something was failing, they knew immediately. Behind the pilots, the flight engineer monitored the engines using a panel that displayed cylinder head temperatures, oil pressure, fuel flow, and manifold pressure for all 4 engines. He could adjust fuel mixture, synchronize propellers, and manage power distribution. His station also included controls for the top turret, making him both engineer and gunner. The navigator, working at a small table in the nose section, used dead reckoning, celestial navigation, and radio direction finding to guide the aircraft to its target and back home. His calculations had to be precise. A navigation error over the North Sea meant death for the entire crew. The bombardier, also stationed in the nose, operated the Norden bomb sight, a precision instrument that calculated the exact moment to release bombs, accounting for altitude, airspeed, wind drift, and target motion. The bomb sight was classified secret. Crews were instructed to destroy it before bailing out or surrendering. The device represented American technological sophistication in mechanical computing, a system the Germans had nothing comparable to match. On April 17, 1943, a B-17F, named the 8-Ball, from the 91st Bomb Group was returning from a mission over Bremen, Germany. The aircraft, piloted by First Lieutenant James Mahoney, had been hit repeatedly during the bombing, a run, and the fighter attacks that followed. The No. 3 engine was dead, its propeller feathered. The No. 4 engine was running rough, losing oil pressure. The hydraulic system had been shot away, meaning the landing gear would need to be cranked down manually, and the brakes would not function. But the damage that should have destroyed the aircraft was in the tail section. A German fighter had made a pass from 6 o'clock low, raking the entire length of the fuselage with 20mm cannon fire. One shell had exploded inside the tail gunner's position, killing Sergeant John Willingham instantly. The blast had torn away large sections of the tail cone. The vertical stabilizer had multiple holes large enough to put a man's arm through. The horizontal stabilizers were shredded. The elevator control cables had been severed on one side and were hanging by a single strand on the other. Mahoney discovered the extent of the damage when he tried to level the aircraft after, leaving the target area. The controls felt wrong. The aircraft wanted to pitch nose down constantly. He had to hold the yoke back with both hands, straining against the force. His co-pilot, Second Lieutenant Gerald Saylor, tried to help, but even with both men pulling, the aircraft barely maintained level flight. The flight engineer came forward to report what he had seen when checking on the tail gunner. The tail was nearly gone. It was hanging by cables and twisted metal. He did not understand how they were still flying. Mahoney knew they could not maintain altitude over the North Sea. The channel crossing required holding at least 5,000 feet to avoid German flak ships. With one engine gone, another failing, and the tail damaged, they were slowly descending. He calculated they might make it to the English coast if they could maintain their current rate of descent. Maybe. He ordered the crew to throw out everything that was not essential: ammunition, empty shell casings, equipment, anything that had weight went out the waist gun windows. The bombardier and navigator came forward to add their strength on the controls. 4 men now held the yoke, taking turns when their arms gave out from the constant strain. The aircraft vibrated violently. Pieces of metal were tearing off the tail, fluttering away in the slipstream. Each piece that came loose changed the aircraft's handling characteristics slightly. Mahoney had to constantly adjust, learning to fly a machine that was changing its aerodynamic properties minute by minute. They crossed the English coast at 2,000 feet, descending through 1,500 as they approached their home field at Bassingbourn. The tower cleared them for an immediate landing. Fire trucks and ambulances were already rolling. Mahoney told his crew to brace for a crash landing. With no hydraulic pressure, the brakes would not function. They would land fast and use the entire runway. The landing gear cranked down, manually locked into place. The aircraft crossed the threshold at 130 miles per hour, far faster than the normal approach speed of 95 miles per hour. The main gear touched. The tail wheel, what remained of it, settled onto the concrete. The aircraft rolled and rolled, eating up runway. At the far end, it finally slowed enough that Mahoney could ground loop it into the grass. The B-17 came to rest off the side of the runway, sitting at an angle with its tail section visibly sagging. When ground crews reached the aircraft and saw the damage, they initially refused to believe it had flown from Germany in that condition. The entire tail section aft of the waist gun positions was held on by approximately 1/3 of its normal structural connections. Most of the skin was gone. The internal frames were visible. The control surfaces had holes you could see through. One ground crew chief later wrote in his official report that he could not explain how the aircraft had another pose, remained airborne. The physics should not have allowed it. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. But the 8-ball was not unique. Throughout 1943 and 1944, B-17 seconds returned to English bases with damage that seemed impossible to survive. Aircraft landed with entire sections of wing missing, the structure blown away by flak or cannon fire, yet still producing enough lift to fly. Bombers came back with 2 engines completely gone, running on the remaining 2, barely maintaining altitude but still controllable. Aircraft returned with the nose section destroyed, the bombardier and navigator dead, the entire front of the aircraft open to the slipstream, yet the pilots still able to see enough through the shattered windscreen to land. Luftwaffe fighter pilots reported their victories according to strict criteria established by Reichsluftfahrtministerium, the German Air Ministry. A bomber was confirmed as destroyed only when it was seen to crash, explode in mid-air, or when crew members were seen bailing out. A bomber claimed as probable was smoking heavily and losing altitude but not observed to actually crash. Damaged bombers that remained in formation or appeared to still be under control did not count toward a pilot's score at all. By mid-1943, German pilots were reporting increasing numbers of probables that were not turning into confirmed kills. Major Egon Meyer, one of the Luftwaffe's most successful bomber-destroyers with over 100 victories, wrote in his after-action report from a mission in August 1943 that he had made 3 separate attacks on a single B-17, expending nearly all his ammunition. He observed hits on the engines, fuselage and wings. He saw pieces of the aircraft break away. The bomber dropped out of formation and appeared to be going down. He broke off to engage other targets. Later intelligence reports indicated that same bomber had landed in England. Mayer was frustrated but analytical in his assessment. He wrote that the American bomber was constructed far more robustly than German intelligence had estimated. The standard fighter armament of 2 20mm cannons and 2 13mm machine guns was proving insufficient. He recommended that fighters be equipped with heavier cannons, 30mm weapons that fired larger explosive shells. He also recommended increased use of air-to-air rockets, unguided projectiles that could be fired from outside the range of the bomber's defensive guns. The Luftwaffe responded to these recommendations by developing the Rüstsatz, or field modification kits. that added heavy armament to standard fighters. The R2 kit for the WWII added two 30mm Mk108 cannons in underwing pods. These weapons fired a much larger shell with greater explosive content than the standard 20mm. A single hit from a 30mm cannon could tear apart a bomber's wing spar or blow an engine completely off its mounts, but the heavy cannons reduced the fighter's speed and maneuverability, making it more vulnerable to the bomber's defensive fire and to American escort fighters that were beginning to appear in increasing numbers. The Wehrmacht 21, an air-to-air rocket, was deployed in late 1943. The weapon consisted of a mortar tube mounted under each wing, firing a 40-pound rocket with a time delay fuse. The rockets were fired from 1,500 yards range, outside the effective reach of the bomber's 50-caliber guns. When they detonated near a bomber formation, the blast and shrapnel could damage or destroy multiple aircraft. The weapon was devastating when it worked, but accuracy was poor, and the rockets often failed to detonate at all. German fighter tactics evolved to focus on attacks that maximized damage in a single pass. Instead of making multiple runs on a single bomber, pilots were instructed to hit it once with everything they had, then move to the next target. This approach recognized that the B-17 could absorb multiple hits from standard weapons, but might go down from a concentrated burst of heavy cannon fire, all striking within seconds. Hauptmann Hans-Joachim Jabs, who flew both day and night fighters and survived the war with 50 confirmed victories, was interviewed extensively by American intelligence officers after his capture in 1945. He described the psychological impact of watching B-17 seconds absorb damage that should have destroyed them. He said that German pilots developed a fatalistic attitude toward bomber interception missions. They knew they would inflict damage. They knew they would shoot down some bombers, but they also knew that many bombers they hit, bombers they were certain they had destroyed, would make it back to England. Jabs mentioned a specific incident from February 1944, where he had attacked a B-17 that was already damaged and separated from its formation. He made a diving attack from above, firing a long burst that struck the bomber's fuselage and wings. He saw his rounds hitting. He saw metal pieces flying off. The bomber's nose dropped. It entered a shallow dive. He was certain it was going down. He broke off to avoid collision and began climbing to rejoin his squadron. As he gained altitude, he looked back to confirm the crash. The bomber had pulled out of its dive and was continuing westward, losing altitude slowly but still flying. He could not believe it was still in the air. The B-17's ability to absorb damage and return home was not abstract engineering triumph. It was measured in lives saved, in crews who walked away from aircraft that should have been their coffins. The statistics compiled by the 8th Air Force tell part of the story. Of the 12,731 B-17 seconds accepted by the Army Air Forces during the war, 4,735 were lost in combat. That represents a loss rate of 37% of all B-17 seconds built. The number seems catastrophic until compared to crew losses. The 8th Air Force flew from England against targets in occupied Europe and Germany from 1942 until the war's end in May 1945. During that period, 26,918 airmen were killed in action. Another 23,000 were wounded seriously enough to be removed from combat status. More than 28,000 became prisoners of war after being shot down over enemy territory. The casualty rates were staggering. A bomber crew had approximately a 1 in 4 chance of completing their required 25-mission tour without being killed, wounded, or captured. But the survival rate would have been far worse in a less durable aircraft. British losses in their night bombing campaign, flying less robustly constructed bombers like the Lancaster and Halifax, were proportionally higher. The Royal Air Force Bomber Command suffered 55,573, killed out of 125,000 aircrew who served, a death rate of 44%. The difference was not in the courage or skill of the crews. British and American airmen faced the same flak, the same fighters, the same terrible odds. The difference was in the aircraft. A B-17 could lose an engine and continue flying. It could lose 2 engines and usually still make it home, though barely. Aircraft returned to England on 2 engines, regularly enough that it became almost routine, though each such return was a testament to both crew skill and aircraft design. Some made it back on a single engine, though these cases were rare and required perfect conditions and exceptional piloting. The self-sealing fuel tanks prevented countless deaths. In earlier aircraft, a single incendiary round in a fuel tank meant instant catastrophic fire. The crew had perhaps 30 seconds to bail out before the aircraft exploded. The B-17's self-sealing tanks would seal around bullet holes within seconds, preventing both fuel loss and fire. German pilots learned to concentrate fire on the fuel tanks, hoping to start fires, but the self-sealing technology defeated this tactic more often than not. Bombers returned with dozens of holes in their fuel tanks, yet no fire had erupted. The redundant control systems meant that severed cables did not doom the aircraft. Pilots learned to fly with partial control authority, compensating for damaged surfaces with trim tabs and power adjustments. Some returned with elevator cables completely shot away, controlling pitch solely through throttle manipulation and trim. The technique was exhausting and imprecise, but it worked well enough to get the aircraft across the English Channel and onto a runway. The armour protection saved countless crew members from wounds that would have been fatal in an unprotected aircraft. Pilots sat behind thick armour plate that stopped machine gun bullets and light cannon fragments. The armour did not make them invulnerable, but it increased their odds of survival significantly. Numerous accounts exist of pilots discovering bullet impacts on their armour plate after landing, rounds that would have killed them had the armour not been there. Staff Sergeant Kenneth Bragg, a ball turret gunner with the 306th Bomb Group, survived a mission over Schweinfurt in October 1943, when a 20mm cannon shell exploded against the armour protecting his turret mechanism. The blast knocked him unconscious and left him with severe concussion and temporary hearing loss, but he lived. Without that armour, the shell would have detonated inside the turret, killing him instantly. He flew 23 more missions before completing his tour and returning to the United States. The psychological impact of knowing their aircraft could take tremendous punishment and still fly affected crew morale positively. Men who might have been paralyzed with fear, knowing they flew in fragile machines, instead developed confidence in their B-17 seconds. They named them, painted nose art on them, developed personal attachments to specific aircraft. This was not mere sentimentality. It was recognition that their survival depended on the aircraft's durability as much as their own skill and luck. After the war ended in May 1945, the Army Air Forces conducted extensive analysis of combat damage to determine what had worked and what had not worked in aircraft design. The study involved examining thousands of damaged aircraft, reviewing maintenance records, interviewing crews and ground personnel, and compiling statistical data on every aspect of bomber operations. The resulting reports filled volumes and formed the basis for post-war aircraft design philosophy. The single most dramatic finding was the confirmation of what crews and maintenance personnel had known throughout the war. The B-17 could absorb damage far beyond what any pre-war analysis had predicted. Aircraft returned with damage that exceeded every theoretical failure threshold. The engineering margins built into the design, the redundant systems, the robust construction, all worked exactly as Boeing had intended, and often worked even better than Boeing's own engineers had dared hope. One particular B-17, serial number 4231083, became famous in the post-war analysis. The aircraft, nicknamed Old Faithful by its crew, completed 83 missions over occupied Europe between March 1943 and April 1945. It was hit by flak or fighter fire on 67 of those missions. Ground crews documented every instance of battle damage. By the war's end, the aircraft had been struck by enemy fire more than 900 times. It had holes patched over holes that had been patched earlier. Entire sections of wing skin had been replaced multiple times. 2 engines had been changed after being shot up beyond repair. The tail section had been rebuilt twice, yet the aircraft never failed to bring its crew home. 83 missions, 67 instances of battle damage, 900 documented hits. Not once did the aircraft fail catastrophically. Not once did the crew have to bail out or make an emergency landing in enemy territory. The aircraft simply refused to quit flying. After the war, it was flown back to the United States and placed in storage. In 1968, it was scrapped, cut apart for aluminum. No one thought to preserve it. There were thousands of B-17 seconds, and at the time, no one imagined they would become rare. The legend of B-17 durability was built on hundreds of such aircraft and thousands of missions, where bombers that should have gone down made it home. But the legend was also built on specific, dramatic incidents that became famous throughout the 8th Air Force and later in aviation history. The story of All-American, a B-17F that collided with a German Bf-109 over Tunisia in February 1943, was perhaps the most visually dramatic. The fighter struck the bomber's fuselage just behind the wings, cutting through the aircraft nearly to the point of severing the entire tail section. The B-17 continued flying with its tail hanging on by a few structural members and some control cables. It landed successfully, and photographs of the damage showed an aircraft that appeared physically impossible to fly. The incident was documented thoroughly because it occurred in daylight with multiple witnesses, and because the aircraft survived to be photographed. But similar incidents occurred throughout the war, many less dramatic visually but equally remarkable from an engineering perspective. Aircraft returned with wings, partially folded from structural damage, with entire sections of fuselage blown away, with control surfaces missing, with landing gear shot off. Each incident added to the legend and reinforced the psychological impact on both American crews and German fighter pilots. The Germans never fully adapted to the B-17's durability. They increased their firepower, they refined their tactics, they developed new weapons specifically designed to destroy heavy bombers. But the fundamental problem remained. American industrial capacity could replace lost bombers faster than the Luftwaffe could shoot them down, and a significant percentage of bombers hit severely enough that German pilots believed they were destroyed actually made it back to England, were repaired, and returned to attack Germany again days or weeks later. By 1944, the cumulative effect of American bomber production and B-17 durability had become overwhelming. The 8th Air Force could dispatch 1,000 bombers on a single mission. Even if the Luftwaffe destroyed 50 bombers, a catastrophic loss rate by any standard, 950 returned to base. Of those, perhaps 300 had battle damage requiring repair. Ground crews worked through the night. By dawn, most of the damaged aircraft were patched and ready to fly again. The bombers that were destroyed were replaced from the steady stream of new aircraft arriving from the United States. Within days, the 8th Air Force could launch another 1,000-bomber mission. When Second Lieutenant Harold Fisher climbed down from his damaged B-17 at Kimballton on that February afternoon in 1943, he did not think he had done anything particularly remarkable. He had done his job. His crew had done their jobs. The aircraft had done what it was designed to do, bring them home. It was only later, when he saw the ground crew counting the holes, when he saw the photographers documenting the damage, when he heard the stunned comments from men who maintained aircraft every day, that he began to understand just how close they had come to not making it back. The B-17 that absorbed 3,000 bullet holes and still landed safely is often cited as the extreme example of bomber durability, though the specific documented case with that exact number is difficult to verify in official records. The number may be apocryphal, or it may be an aggregate of multiple severely damaged aircraft whose stories merged in the retelling. But the essential truth behind the legend is verified in hundreds of mission reports, damage assessments, and crew testimonies. B-17 seconds routinely returned with damage that seemed impossible to survive. The legacy of the Flying Fortress extended far beyond World War II. The design philosophy that prioritized crew survivability and system redundancy became standard in American military aircraft design. The B-52 Stratofortress, which entered service in 1955 and remains in service today, 7 decades later, was designed with the same philosophy: robust construction, redundant systems, and the ability to complete the mission despite battle damage. The lessons learned from B-17 combat operations influenced every American bomber design that followed. For the men who flew B-17 seconds in combat, the aircraft became more than a machine. It was the thing that stood between them and death. They trusted it in ways that only combat can create. They knew its sounds, its vibrations, its handling characteristics in every possible condition. They knew that if they did their jobs correctly, if they flew with skill and maintained their aircraft properly, the B-17 would bring them home. Most of the time, it did. The German pilots who fought against the B-17 remembered it differently. For them, it represented the moment when they understood that the war was already lost. When a fighter pilot could hit a bomber repeatedly with cannon fire, see pieces of the aircraft flying off, watch it drop from formation smoking and damaged, and then learn later that same bomber had landed safely in England, it destroyed the illusion that superior tactics and individual skill could overcome material disadvantage. The B-17 was the physical manifestation of American industrial power. It could be damaged, but not easily destroyed. When one was finally shot down, another appeared to take its place, and another after that, and another. There seemed no end to them. The psychological impact of this realization on German fighter pilots has been documented in numerous post-war interviews and memoirs. They described a growing sense of futility, of fighting against odds that could not be overcome. Individual victories meant little when American bomber formations kept growing larger, when the bombers themselves seemed nearly indestructible, when American escort fighters eventually appeared to protect the bombers all the way to targets deep inside Germany and back. By late 1944, Luftwaffe day fighter operations had largely collapsed. The survivors were either killed, captured, or withdrawn from combat, as fuel shortages and pilot losses made continued operations impossible. The B-17 Flying Fortress was not invincible. 4,735 of them were destroyed in combat. Tens of thousands of airmen died or were wounded while flying them. The aircraft had vulnerabilities, limitations, and failure points, but it could absorb battle damage beyond what any other bomber of its era could survive, and that capability saved thousands of lives. It was the difference between a crew bailing out over Germany to face death or capture, and that same crew landing safely in England to fly another day. When ground crews at Kimbolton finished counting the holes in Lieutenant Fisher's B-17, when they documented every instance of damage, when they compiled their report and sent it up through channels to 8th Air Force Headquarters, and eventually to Boeing engineers back in the United States, they were not just recording data. They were confirming a design philosophy. They were proving that building aircraft to bring crews home, even at the cost of speed or payload or other performance metrics, was the correct choice. They were validating every decision Boeing engineers had made when they designed redundancy, robustness, and survivability into every system. The B-17 that absorbed extraordinary damage and still flew was not a miracle. It was applied engineering, industrial capacity, and design philosophy made manifest. It was the physical proof that American manufacturing could produce weapons that matched the courage of the men who used them. It was the evidence that in industrial warfare between modern nations, production capacity and design quality matter as much as tactics and training. The Germans learned this lesson the hard way, watching bomber after bomber that should have fallen from the sky continue flying westward, toward England, toward home, toward another mission tomorrow. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now and don't forget to subscribe.